Good afternoon, everyone. Hope you guys are doing well. This is unfortunately and very sadly for me as well, our last day of the learning space winter school. It's been an awesome journey working with you guys and helping you guys prepare for your upcoming exams. This is not the last time you will be seeing us, however, we will have another series of these lessons coming up from the beginning of August. So we're going to take about 2 weeks off, and then after the 2 weeks break, we're going to then catch up and do our prep for prelims. Awesome, guys. Before we get started, just a warm welcome to everyone on Zoom, warm welcome to everyone on TikTok. Guys, please remember golden rules. It's an interactive session. Please make sure that you guys do take part in the session. How do you take part in the session? There's three ways. Number one, there's the chat function. Oftentimes, I will ask you guys questions. And when I ask you guys questions, what I need you guys to do is to respond in the chat. So I'll ask you a question. Which one do you think it is? Is it A or is it B? And then you guys will just post A or B in the chat, right? Cool. The next one is we're going to use our reactions. So on Zoom, we've got reactions at the bottom where you can give us thumbs up emoji, fire emoji. Oftentimes, I like to celebrate small wins. So whenever we get a question right, I'll say, listen, let's all celebrate. Let's all celebrate getting the question right. Or if you didn't get it right, but you did see where you went wrong, that's cause for celebration. And then you'll use the reactions button to get reactions down at the bottom. Finally, we'll have a Q&A on Zoom. The Q&A is for any questions that you want to ask. So please, if I can distinguish between those two things there, if you want to ask a question, use the Q&A. If you want to just respond, make a comment, you can use the chat. The Q&A is something that I see easier than the chat. So if your question is very important, make sure it's in the Q&A. Some things do get lost in the chat. So please make sure we do that. There are a lot of us in the session, so it's important to use those particular features. If you're joining us on TikTok, welcome, welcome, welcome. You might not have all the features, but you do have a chat. So use a chat feature for everything in that case there. I need to get my phone on TikTok so I can actually see these questions here on TikTok. Give me 2 seconds to get that running, and then I'll be with you guys shortly. Okay. Awesome. I've got my learning space live up. I can see your guys' questions. VH20 says, hello, I'm in grade 12. Hello, VH20. I don't know what your full name is, but a very big hello to you. Welcome. If it is your first time, big welcome with the Learning Space family. We do welcome you. We want you to feel welcome. Please click the follow button and make sure you watch more of our videos. Really do appreciate it. All right. Just to make sure that everyone is on board, we get the interaction. Let me see some reactions. Let me see some fire emojis, dancing emojis in the chat. Let's make sure that everyone is here with me before I get started. Give me some good reactions there in the chat. Good reactions. There we go. The reactions are coming through on Zoom. Well done, well done, well done. And some love in the chat as well. Then I know I can get started. Fantastic. Okay, great reactions there. Awesome, guys. Okay, give me 2 seconds to get my screen share up, and then we will get started. While I do that, if you've got a friend that you know should be in the session, just send a reminder to all your mates. Say, listen, class is in session. It's the last winter school session. Better not miss it. So please make sure you join. If you're on TikTok right now and there's a friend who's like going to really appreciate this session, please ask them to join the session shortly. Awesome. Okay, I'm going to get my writing pad up. Give me 2 seconds. All right. And then just to help you guys save some data, I'm going to switch my video off just to help you guys save data. And then we're going to get started. Fantastic. Guys, I do have a bit of construction happening where I am. So if it does get noisy, just someone do let me know, and then I'll try and see what plan I can make just to rearrange where I'm seated. All right. Cool. Welcome to Learning Space Winter School. This is the last session. We're doing electric circuits, getting you guys ready for term 3. All right. So let's quickly go through some of the notes. We're going to kick off with some definitions. And then once we've nailed our definitions, we're going to then spend most of our time today doing problems. I'm not going to spend too much time on the definitions and the notes as such, right? I think electric circuits is a topic that's best practiced by doing it. That's going to be the way you really get to learn it, right? Okay. I'm going to get started. And then just a final reminder, right, in terms of how to go about your interactions. When you want to ask a question in the Q&A, one thing I'd really advise you guys to do is Don't say, sir, please repeat, or sir, I don't understand. You need to ask what I refer to as really smart questions. So smart questions are, sir, when solving 1.3, I was with you up until the second step. I got lost at the third step. I don't know how you changed from this to that in the third step. So if you give me very specific questions, it helps me to answer you better, number one. Number two, it also helps me to pinpoint where your misconceptions are. And then once I know your misconceptions, I can really help you. Those that have been in the sessions before understand that when someone does ask a question, I tend to go around and try fill in more than what you've asked, just because I need to be able to fill out any misconceptions that you would have in particular. So let's make sure we ask really constructive questions, right? So basic definitions, we'll start off with current, right? So this is a topic that you guys have been learning from grade 10, some even earlier than that. So I'm gonna speed up where I need to speed up and then slow down where I need to slow down. If I am going too fast at a point, just say, sir, please slow down. I'm not following with you, and I will do that just for you. Awesome. So the current is the rate of flow of charge, right? Remember, when we're dealing with electric circuits, charge is going to be carried by the electrons that flow through our circuit, through our conductors. And then the amount of charge carried by those electrons per unit time is going to be what we refer to as our current. So the current is measured by a device called the ammeter, right? The ammeter is connected in series. So you'll always see the ammeter in the main part of your circuit because it has a very low, what you can basically call negligible resistance, right? In that case there, it looks like that circle with an A in it. That's how you identify an ammeter, all right? Then we've got potential difference, or some would just say voltage, right? So potential difference is the energy required to move a coulomb of charge between 2 points. So when you think of those electrons going from point A to point B, how much energy is required to move them, to move 1 coulomb of charge from point A to point B is what we refer to as the potential difference, right? It's measured using V is equal to W over Q, where V is my potential difference, and then W is my work or energy. And then Q is going to be the charge, right? That is moved across those 2 points there. This potential difference is measured by a device we refer to as a voltmeter. Voltmeters must always be connected in parallel because they've got a very high resistance. For the purposes of learning it in grade 12, you can assume that a voltmeter has infinite resistance. So no current will flow through a voltmeter at all. So imagine current flows very easily through an ammeter. None of it gets used up. And then current does not flow through a voltmeter. It's got very high, almost infinite resistance, right? Okay. And then resistance is simply the extent to which the flow of current is opposed. It's a thing that slows down that current as it flows through. The higher the resistance, the less current will flow through. The less the resistance I have in my circuit, the more current will flow through. Remember that your current always flows through the path of least resistance. So when you get parallel junctions, the side with more resistance will have less current. The side with less resistance will have more current, right? That's generally how it works. And then the last definition we're going to go through there is our EMF, right? Our electromotive force. It's very similar to our potential difference, except in this case, we're referring to the battery. So think of EMF when you look at the word electromotive. Electro talks about electrons, motive talks about moving. So it's a force that moves electrons through my circuit, right? So the definition of EMF, it's the energy provided per coulomb of charge that moves through the cell. That's the important thing about electromotive force. You'll see it's very similar to our potential difference. Now, when they tell us that an EMF or a cell has an EMF of 6 volts, what they really mean there is that 6 joules of energy will be given to each coulomb of charge. So when a coulomb of charge goes out, it'll have 6 joules of energy. If I had an EMF of 12 volts, it means I'll have 12 joules of energy given to each coulomb of charge in that case then. Key definitions, I'll always remind you guys, definitions are super important, guys. Don't leave those out. There's a lot of marks within definitions. You'll see when we do our problems just now. And oftentimes, when you know the definition, the next question is going to rely on you utilizing the definition or the equation of that definition. So when you know your definitions well, you're gathering lots and lots of marks. Awesome. So from there, we're going to learn a little bit about Ohm's law, right? Which is one of the main laws we use in electric circuits. So Ohm's law says that the current through a conductor is directly proportional to the difference across its apologies, like terminals or anything across like that, provided the temperature remains constant, right? So your current is directly proportional to the potential difference, provided the temperature remains constant. So V is equal to IR, meaning V is directly proportional to I in this particular case when temperature remains constant. Then we can get there and start talking about ohmic versus non-ohmic conductors. So an ohmic conductor is one that follows Ohm's law. All right, that follows Ohm's law at a particular temperature. If a conductor does not follow Ohm's law, we refer to that as a non-ohmic conductor. So, for example, here's an example of a non-ohmic conductor. We're talking about the filament in a light bulb, an incandescent light bulb. Let me just be very specific about that. That is a non-ohmic conductor. And then an ohmic conductor is copper wire. Ayabonga's got a hand up. Let me pause here and then allow you to ask your question. So Ayabonga, just click unmute on your side, and then you can ask your question. Aya, go ahead. We're listening. Ayabonga, we are listening. You are unmuted. Just ask your question. If not, I'm going to just mute you again so I can continue with the class. Okay. While I'm paused, let me just see if there's any questions at the moment. TikTok, nothing there. Q&A is empty. Okay, in the chat. Bonolo, thanks for your question. Please remember, guys, if you want me to see your questions as quickly as possible, put them in the Q&A, not the chat. Because in the Q&A, they pop up for me, so I'll see them immediately. In the chat, they get lost in all the other conversations that happen in the chat, right? Okay, but anyway, Bonolo's asking, sir, can you please repeat how EMF is different from potential difference? 100%. And thank you for your very specific question. I love questions like that. So potential difference, right, is the energy required to move a coulomb of charge between any 2 points. So from a circuit, let's imagine, let me go scribble somewhere. So if I had a circuit here and that circuit, I've got a cell, I've got a resistor here, I've got a resistor there, I've got an ammeter there, and then my cell is complete, right? So if this is a setup that I've got here, right? So potential difference is basically the amount of energy required to push a coulomb of charge between any 2 points. So I could choose the 2 points. I could say this is point A and this is point B. So how much energy do I require to push 1 coulomb of charge from A to B? That is the potential difference at that point there. I like to think about it as the electrical potential energy difference. So it's what's required. Think about it as the amount of energy required to push charge from A to B. To move that current from A to B, how much energy is required per coulomb of charge? That's what potential difference is, right? So even if you had to move it from B and then we said C, that's going to be a different amount of energy that's required to push a coulomb of charge from B to C, and then maybe from C to D, and maybe from D all the way back to A. That's potential difference. It's the V we use when we're doing electric circuits, all right? Now, EMF, I want you to think around particularly your cell or your battery, right? So it's the energy provided per coulomb of charge that moves through the cell. So basically, it's how much energy the battery can give us per coulomb of charge. So not necessarily how much is required to move from A to B, but it's the total amount of energy that my battery can push out per coulomb of charge. So that's what EMF is. It's how much energy my battery can give versus potential difference is simply asking how much energy is required to move from A to B. So potential difference in that case there might not be the same as EMF, right? So even though you might need 2 volts to get from A to B, your battery could have a 12-volt EMF. As long as your battery has got more EMF, then the potential difference is required. That's the key difference. Bonolo Ayabonga, I hope that makes sense to you guys. So one refers to just pushing charge through from point A to B. The other one talks about how much energy can my battery push out entirely to move that coulomb of charge out of the battery or through the cell, right? I hope that makes sense to you guys. Okay. And then Sponogutha says, aren't we able to hop in the screen? I don't know what that means. So, but you can type your question in full, or what you can do is you can put a hand up and I'll allow you to unmute and then you can ask live because I'm not really sure what your question's asking. Sponogutha. Okay, I'll wait for that there. Guys, another reminder, please, 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 ask your questions in the Q&A. So if you look at the bottom of your screen, if you don't see Q&A at the bottom, press the three dots to get more options, and then you'll see Q&A. Put all your questions in the Q&A. They will get lost in the chat, especially as we go through the lesson and there's more interaction. I don't want to miss any of your questions. Please, please, please. Okay, awesome. So we've done Ohm's law as well. Now let's have a look at resistors, right? So we'll first look at working with resistors in series. So now, working with resistors in series, we refer to these as potential dividers. So resistors in series will divide my potential difference, right? There's a law that if you do physics in first year that you learn, we apply it in grade 12, but we don't really have a name for it, right? But basically, it's going to be your KVL, your Kirchhoff's voltage law, right? Which normally refers to that in a circuit, the sum of the potential difference providers. So if you think about like all your EMFs in a cell must equal all your volt drops in a cell, right? But there's a version of it that we apply where we can see that when you're looking at potential difference, you can essentially just add it up in series. So if I've got potential difference, let's call this V1 across resistor 1, 2, and 3. Let's call that R1, R2, and R3. So when I've got this potential difference V1 over R2, R1, and R3 as 32 volts, right? And I go and measure the individual potential difference on R1, R2, and R3, right? Let me first actually call this VT, right? And I measure this V1 for R1 and V2 for R2 and V3 for R3, you'll find that they will add up to V total, right? So your potential difference over things in series should add up to the individual potential difference. And that makes sense, right? Let's go back to the definition of potential difference, right? Potential difference is the energy required to move a coulomb of charge between any 2 points. So if we come back here, what we can see is that if I need 4 volts or 4 joules per coulomb to move it from point, let me label these points, point A to point B, and I need 8 volts or 8 joules per coulomb to go from point B to point C, and I need 20 volts or 20 joules per coulomb to go from point C to point D. If I simply add all of those up, it's going to be 20 plus 8, which is 28. 28 plus 4 is going to give me 32. Then you can actually see, oh, actually, if I go from A straight to D, it requires 32 volts or 32 joules per coulomb to do the exact same thing. And that's an important thing to look. So when we talk about resistors in series being potential dividers, we mean that the potential difference in series is going to be shared, right, amongst all of the resistors, which is going to be different to parallel. Where parallel, we're dealing with now current dividers, and you'll see what that means. So my current in series is exactly the same. So if I can give you a quick little summary here, my V total is going to be equal to V1 plus V2 plus V3. So potential dividers are resistors in series. But my current, what you'll see there is the current through resistor 1, A1, the current through resistor 2, A2. Oh, let me fix that. The current through resistor 2, which is A2, and the current through resistor 3, which is A3, are all equal. A1 is equal to A2 is equal to A3. So in series, your current will remain the same, all right? But your potential difference will be different. unless the resistors have the same value. If they have the same value, they will have the same potential difference because they will require the same amount of energy per coulomb to push electrons or to push charge through them, right? So in this case, that's a key thing to note. So as a quick reminder, resistors in series, we refer to them as potential dividers because they will divide our potential difference. But when you add up the potential difference of each individual component, it should be equal to the potential difference of the entire the entire series component that you're dealing with there, or that series I don't want to say string. The word just literally just left me. But that series branch, there we go. That's the word I'm looking for in that case there. So, and another thing to note as well, the potential difference splits in proportion to the resistance, right? So you can see there that the smaller resistance gets the smaller potential difference. Why? Remember, current moves through the path of least resistance. So if there's less resistance, the current can more easily flow through. It requires less energy to go through. The 4 ohm resistor needs 8 volts, right? So you can see there, my 4 ohm resistor is 4 times as obstructive as the 2 ohm resistor, and it therefore requires 4 times the energy per coulomb. It doesn't require 4 volts, it requires 8 volts, right? That's Ohm's law at work. So the more resistance I've got, the more energy I need to push a coulomb of charge through point B to C. And then 10 ohms is 5 times, right, as resistive as 2 ohms, and therefore requires 5 times the energy to push current through as the 2 ohm resistor. Hope that makes sense to you guys as you guys are seeing it. I'm going to pause quickly to see if there's any questions. If there are no questions, please give me a thumbs up in the chat so that I know you guys are with me, or some reactions, smiley reactions, thumbs up reactions so that I know you guys are with me and I can carry on. Okay, thanks for the reactions coming through there. Okay, no questions in the chat, no questions on TikTok. I think I can move on. Okay, Mantume says I got lost. Mantume, if you were not there at the beginning of the session, one of the things I said to ask really constructive questions is to tell me very specifically. So saying I'm lost, I don't understand, please repeat, doesn't help me to help you. And I would really love to help you, right? So for me to help you, you need to tell me where you got lost. What do you not understand very specifically? And then I'll try and patch that up for you. And then just put that in the Q&A. I would really appreciate that. So quick reviser, again, resistors in series, we refer to those as potential dividers. So your potential difference, which again, as we mentioned, is the energy required to push 1 coulomb of charge from 2 points, from point A to point B, right? So here we needed 4 volts or 4 coulombs per charge. Here we needed 8 volts or 8 coulombs per charge. There we needed 20 volts or 20 coulombs, 20 joules per coulomb. So then to do the same thing just from A all the way to D, I need 32. So I can simply just add that, and they will give me that value there. That's why I said VT, which is the value of this voltmeter, is going to be equal to V1 plus V2 plus V3 down there. But what's important is that in series, my current remains the same, right? So current through R1, A1 is equal to the current through R2, which is A2, and the current through R3, which is A3. The current is the same. Current only splits in parallel, potential difference splits in series. Okay, so let's look at the opposite. Let's go look at now parallel circuits and how we deal with those in that case there. So we can see up here, this is the summary of what I was telling you guys about. So the total resistance, we simply go R1 plus R2 plus R3. That's how you work in series. The current is going to be all the same, right? The potential difference, if you add them up, you get the total potential difference. How does that differ when we are dealing with a parallel circuit? So in a parallel circuit, what we can see there, we refer to this as a current divider. That's what I told you guys earlier. So in a current divider or parallel circuit, we add the resistance slightly differently, right? Sorry, there's a question from Tammy. Tammy says, so why is it that when more resistors are added in series, the total resistance increases and the total current decreases? Tammy, that's purely because of Ohm's law, right? So first of all, the total resistance in series is equal to R1 plus R2 plus R3. So when you add a resistor, the resistance will increase. But remember now, when you increase the resistance, Ohm's law says the resistance and current are going to be inversely proportional. right? So what's going to happen there is that the more resistance you have, the more it opposes the flow of charge. So you're going to have less current. So meaning less charge is flowing through per unit time, essentially. So as you slow down my flow of electrons, that's what my current is. I have less current through my circuit. Tammy, I hope that makes sense to you. And then someone says, how does the potential difference split according in proportion to the resistance? I mentioned that previously as well. So it splits in proportion because remember what potential difference is. It's the amount of energy required to move 1 coulomb of charge through 2 points, right? So basically, when you look at your potential difference, it's going to be purely dependent on your resistance. The more resistance you have, the more energy you require to move charge through that resistor. The less resistance you have, the less energy you need to push charge through that resistor. So in that case, the more resistance, more potential difference. Less resistance, less potential difference. So it'll split within the proportion of that resistance. More gives you more, less will give you less. Anonymous, hope that makes sense to you. Okay, resistors in parallel, we refer to those as current dividers. I showed you guys now how to add them. So when we add them, right, so we're going to say 1 over R parallel, so 1 over the total parallel resistance equals 1 over R1 plus 1 over R2 plus 1 over R3, right? Please note that R1, R2, and R3 are not the individual values of the resistors, but it's the individual values of the branch total resistance. I'll show you exactly just now what I mean by that, right? Just keep that in mind. So it says they were R1, 2, and 3 are the resistances of each of the branches, not the resistors. All right. So again, then we end up with this I in equals I out. And that's another thing where if you do physics in next year, in first year, you will learn about Kirchhoff's current law, which tells you that all the current into a junction is equal to all the current out of a junction. You've never heard the law being said to you, but you actually apply it every single time you do electric circuits. All right. So, and then that I'll show you again when we look at an example just now. And in parallel, your potential difference is going to be equal, right? So your current is split, but now your potential difference is going to be the same. That's a key thing there, right? So again, note, the more branches I have, the less effective my resistance becomes, regardless of the resistors in each branch. Now, when we've got a situation that looks like this, notice how now I have 4 amps of current going in. That 4 amps needs to split into 1, 2, and 1. Very important. This plus that must equal my 4 amps. So all the current in must equal my current out. And this is the junction I'm referring to. So current comes in this way and it leaves out the other way. So you'll get current this way. It'll go there, it'll go there, it'll go there. And it's going to split in proportion to the resistors, right? So when it splits in proportion to the resistors, what that means is that the most current goes to the least resistor, to the smallest resistor, or the least resistive branch. The least current goes to the most resistive branch, right? That makes sense. Manduma says you're too fast. Please, if you're getting lost, just give me a shout in terms of where exactly you got lost. And also, Manduma, I need to get through the theory so I can get to the questions. And I think don't panic too much. When we get to the questions, we're going to get to apply them nicely. And then you'll see there step by step how we apply them. The theory, when you're doing electric circuits, can sometimes feel a little bit hairy. But once we're done with the theory, the questions will put you at ease. In the questions, Ohm's law, Ohm's law, Ohm's law, Ohm's law, Ohm's law. That'll get you from here to an A in this topic, right? Okay. So as the current goes in, 4 ohms goes in, it's going to split, right? When it splits, it must remain 4 ohms, just that it's going to be like 4 ohms in terms of 1 plus 2 plus 1 gives you 4. So I haven't lost anything there. The current in did equal my current out. Then on the other side there, I'm going to still have 1 ohm coming in. I mean, 1 amp coming in, 2 amps coming in, 1 amp coming in at the bottom, and that will give me my 4 amps back again. Current in must equal current out of a parallel junction. Right? Hope that makes sense. Now, let's look at how we're going to calculate the effective resistance of this parallel junction. If you are ready to get started, you can do the question by yourself. In the meantime, I'm going to do it with everyone else together, right? So keep in mind again that 1 over R parallel equals 1 over the resistance in branch 1 plus 1 over the resistance in branch 2 plus 1 over the resistance in branch 3, right? How do we go and actually implement that? So then what we do is if I'm going to call, let's say oh, sorry, that wasn't meant to happen. If I call this branch 1, that branch 2, and that branch 3, the resistance in branch 1 is 2 ohms plus 6 ohms. So that's going to be 2 plus 6 there. Branch 2 is going to be 4. Branch 3 is going to be 8. That's how you actually do the calculation for a parallel branch, right? So that's why I said it's the resistance of the branch, not the resistance of the resistors. Because sometimes people will then say 1 over 2 plus 1 over 6 plus 1 over 4 plus 1 over 8, and there you'll get the wrong answer. So it's important to do the right thing where it's 1 over the branch, not 1 over the resistor. Very, very important. I'm going to quickly pause for questions and then before we move right on. I'm not going to solve that entire thing, but I want to show you how you do that calculation. And then we'll do the solving when we do our problems just now. Okay, there's a question here. So why is the potential difference the same in parallel? I will show you that just now. And why does the lesser current pass through the branch with the highest resistance, i.e. 1 amp passes through 2 and 6 ohms? As I mentioned before, the current follows the path of least resistance, right? So remember what current is. Let's go back to our definition. Current is the rate of flow of charge. So how much charge passes there per unit time. The more resistance I have, it slows my current down. So what I want you to think about with current is that, so when I say I've got less current going through, right? What I mean is that there's less charge going through per unit time. So my current slows down in a branch with very high resistance. And my charge speeds up in a branch with very low resistance. So when we come back to what we were looking at there, right? The 8 ohm branches have very high resistance. So my charge moves very slowly there. That's what a slow current is. It's like a low, think of current as your charge velocity. It's the velocity that your electrons move through. So a high current is a high electron velocity. A low current is a low electron velocity. So when I've got high resistance, it's like going on a road with very high traffic. I can't move that fast if there's too much traffic. But if my road, like the 4 ohm one in the middle, has very little traffic, I can drive quite a lot faster. You see that this road here has half the traffic as the 8 ohm, which means I can drive twice as fast. So that's what current is. Think of current as your electron velocity, if that helps you visualize it a bit better. So when I've got less current, it means I've got less electrons per second going through there. If I've got more current, I've got more electrons per second. They can move faster through my individual conductors. Okay, and then so please show the notes on parallel circuits. I'd like to screenshot quickly. Please note again, I will share my notes at the end of my lesson. So I have to zoom out quite far. I don't know if you guys will be able to see it, but I am going to share the notes in the WhatsApp community as soon as the lesson's done. So you should be able to just get that and take it from there, right? Okay. I think I've covered all of the questions here. The one I need to cover now is why is the potential difference the same in parallel? And to do that, I would like to do a fun little simulation with you guys. Before I do that, let's quickly cover internal resistance and power, right? Then I'll do my little simulation with you guys. So with internal resistance, R, this is the energy needed to move current through the cell itself. Don't confuse this with your EMF. So internal resistance, basically think about 2 seconds. People are asking, how do they join the WhatsApp community? If you go to the chat and you scroll up in the chat, there was a link that was pasted. I'm not sure if it's Taffy or Arabila who's adminning today, but please maybe just repost it in the chat so that they can see it right at the bottom there. Someone also said, I'm not in the WhatsApp community. Yeah, so they'll post the link for you guys so you can see the WhatsApp community there. Awesome. So think about this. Some of the EMF used to move current through the cell right? Um, and the rest of it is actually going to go out into the external circuit, which is very, very important, right? So your EMF is equal to V external plus V internal. What that refers to is the EMF is remember, that's the total energy per unit coulomb that the battery can push out. My V external is the energy that makes it out of my battery per unit coulomb. My V internal is the energy that was used to push those electrons out. For the battery to work, it needs to use its own energy for it to be able to move, right? Think of even like a car. Like a car you'll put petrol and the car has a battery. And as you're busy, the car needs some energy just for it to function, just for your lights to work, your indicators to work. There's energy required for the car to just be a car. And then whatever is not used in the car is then used to drive the car. That's whatever's left is used to drive the car, which is very important. So you guys will see if you've ever been in a car with a very small engine, um, and you've put the aircon on, you'll actually feel how the car slows down when the engine is on. And then I used to, in my small car, when I'm driving uphill, have to always switch the aircon off so that I can have more energy used to drive the car and less energy used to just sort of having the car be a car, essentially, right? So that's what, think of your internal resistance as that. It's some energy will get used up inside your cell to make the cell be able to work as best as possible in that case there. So again, the equation we use there, the most important one, I'll quickly highlight and I'll draw it for you guys. It's going to be this one here. EMF is equal to I at a simulation as soon as I'm done with this here. And then it'll hopefully make more sense to you guys before we jump into our questions. All right. Then how do I know when what is happening? Right. So two key things. When you have a circuit, right, with a voltmeter over your cell or your battery. So let's say there's a voltmeter here, right? When my switch is open, when S is open and current is not flowing through my circuit, that voltmeter will give me the value of my EMF. However, if this switch were to be closed in this fashion there, that voltmeter will give me the reading of V external. Keeping in mind, V external is the energy per coulomb that makes it out of my cell that my circuit can actually use. That's my V external, right? Whereas my V internal, or what we call our V lost, that's what gets used by the cell for it to be able to work, right? Okay, sorry, just quickly pausing for questions. It's fine. Someone says, can you also do internal circuits? Anonymous, I'm not sure what you're referring to by internal circuits, unless you're talking about internal resistance, right? Which is what I'm busy with now. So very important thing, how to identify which value of V you're getting. If my switch is open or my current is not flowing through my circuit, what I see on that voltmeter around my battery or my cell is our EMF. When my switch is closed, however, the value that my V or voltmeter around my battery or cell will show is V external. It's the total energy per coulomb that actually makes it out of my cell or battery that my circuit can actually use in this case. It's the usable energy, whereas EMF is total energy, not all of it is usable. All right. And then you can see with the closed switch there, that's our closed switch there. Our V external, right, is 5 volts, V internal is 1 volt. Or you can also refer to this as our V lost, right? That's our V lost. Okay, and keep in mind your EMF is going to be equal to V external plus V lost or V internal. So at 5 volts, which is your V external, and your 1 volt, which is V internal, when you add them up, you get 6 volts. And we were told there that our EMF is 6 volts. Very, very important to note that. All right. Okay. Another question in the chat says, please explain the difference between V internal and V external and how to distinguish between the two. 100%, I'll quickly repeat what I was saying now. So V external is the amount of usable energy that gets out of my battery. So how to identify that in a question, and I'll show you guys when we're working there with the question. If you've got a voltmeter that's sitting around your battery or your cell, and you've got an open switch in your circuit, right? Open switch in your circuit, the reading on that voltmeter is going to be equal to EMF. So if no current is flowing, the total potential or the total energy that my battery has is going to be shown in that V external. But if I then close the switch, current starts to flow, which means the battery will work. It will do work in getting the energy out of the battery. And now, because it has to do battery work, some of that energy will get used up in my V internal. And in that case, the reading I'll get on my voltmeter is going to be V external. And if you want to find out what your V lost or V internal is, you can simply use this equation here to find it. EMF is equal to V external plus V lost. So if you said EMF minus V external, that'll give you your V lost. Okay, hope that makes sense. Like I said, it'll make more sense when we start doing the questions there. Okay. Okay, someone says, Novio says, so please explain and show us when the voltmeter on the battery will read 6 and when it'll read 0. So the voltmeter on the battery will never read 0. Novio, that's an important one, right? So the voltmeter on your battery will only ever give you one of two values. It'll either give you your EMF or it'll give you your V external if it's connected to both terminals of the value. So it'll either be 6 or it'll be 5 in this case, but not 0. Even when the switch is open, you're not going to get 0. When the switch is open, you're going to get you're going to get EMF. When the switch is closed, you're going to get your V external. That's very important to note there. Thanks for the question. Okay. Then we've gone through that there. I'm going to skip that graph so we can quickly go look at power and our simulation. So again, power, the rate at which work is done. For example, how quickly electrical energy is turned into light and heat by a light bulb, right? So the more power equals a brighter light bulb. So power, by definition, is the amount of work per unit time, W over T, right? Someone asked there, why is V internal 1? It's just the value that it was. It was an example value. So you'll always have to either calculate it or anything like that. In this case, it was an example value as given as 1. The most important thing to show there was that your V lost or V internal plus V external must equal EMF. All right. Okay, so what I want to do now quickly with you guys, I want to do a quick little simulation, right? Give me 2 seconds just to set it up. And then we'll be able to then start exploring these different concepts I've been telling you guys about as we go through it, right? So I'm quickly going to just go to FET simulations, and then you guys will be able to then see what we're working with there. So let me quickly get a circuits demonstration going on there. Okay, so this is a fun little simulation. If you don't get to do experiments at your school, you can use PHET. You'll see bottom right corner of my screen. It shows you the PHET, which is a FET simulation. And you can actually go and visualize some of these things here and actually go play around with them, right? So as you do that, I'm going to show you guys now on our side how we engage with some of these concepts I've been teaching you guys about. So let's quickly build a circuit. My circuit requires a battery. Let's pull the battery in there. I need some wires on my battery. I'd like a switch in my circuit. What I want is a resistor. Let's get another wire there. I want another resistor in parallel. I want another resistor in series. And then let me just quickly finish off this circuit as we have it. Okay. Notice again, let me zoom in a little bit. Ooh, sorry, I wasn't meant to do that. Let me zoom in a little bit. Notice now how we don't really have any current flowing, right? Reason being, our circuit isn't complete. I need to close my switch first. See, now that I've closed my switch, my current is going to start flowing. So as we see there, my current is flowing in my circuit because I have now closed my switch. Let me zoom in a little bit just so you guys can see it better, right? So it's flowing at a particular rate. Now I'm going to do something, right, where I'm going to increase the EMF of my cell. Let's increase the EMF of my cell. It's currently 9 volts, and I'm going to make it something big. Like, there we go, 40 volts. Notice the difference. Notice how now my electrons are moving quite a bit faster through my battery, quicker than they were moving before. I'll quickly show you again. I'll drop them right down to maybe 3 volts. Look at how slow they're moving now, right? But if I increase it there, 50 volts nearly, they're moving quite quickly. So the greater my EMF, the faster my charge moves through my cell. It means I'm going to have more current. So remember what I said? Think of current as your electron velocity, right? So electron velocity is like how fast my charge is moving through this cell. I'm going to quickly pause for questions. Guys, please remember, to put your questions in the Q&A because I do miss them in the chat with all the interaction that's happening there. Someone said, would I be correct to describe power as work done per unit time? 100%. Jorge says, is this an app, sir? PHET simulations. It's a website and an app. So I'm not sure. I know on the app store, the Apple App Store, it is there. I'm not sure about the Google Play Store, but you can definitely check it out. But on any internet connected device, just go to just Google PhET simulations and you'll get it. And it's got lots of little simulations that you can actually use, right? All right. So that's one thing I wanted to show you guys is that the difference in how the potential difference works. Now, the next thing I want to show you guys is how current moves differently through different resistors. I'm going to first remove this resistor just so I can simplify my life a little bit, right? So at the moment, our resistors have the very same value. So if you look at the current through my two resistors, they're going at the exact same speed, right? So we have the same current. My electrons are moving at the same speed through my two resistors. So what I'm going to do, I'm going to change the value of one resistor, and you can then see how that changes the current that flows through it. So I'm going to take the top resistor, and I'm going to make that's 10 ohms, and the other one is also 10 ohms. You can see there. I'm going to make the top one 10 times. I'm going to make it 100 ohms, more or less. Now you can see when I zoom in, look at the speed of the electrons on the 10 ohm resistor. That's the one at the bottom. This is the 10 ohm resistor here at the bottom. They're moving quite quickly. But look what happens when the electrons get to my 100 ohm resistor, right? Someone is asking, why does it change with the resistance? It's because the high resistance really opposes my flow of charge. It slows my current way down. And then you have very low current at the top here in my 100 ohm resistor, but very high current in my bottom 110 ohm resistor, because electrons or current will always prefer to flow down the path of least resistance in that case there, right? And then another thing I want to show you, sometimes you'll get a question, they'll say, what happens if a cable of negligible resistance then goes and connects two particular points, right? In that case, I need to bring my series resistor back. Let me quickly bring that series resistor back, right? And then let me bring this resistance back down to something useful. Okay, so what I'm going to do, I'm going to take a wire, and I'm going to take that wire and join it here and there. So here's one thing I want you guys to see now, right? In the simulation. The current goes through my battery, down the first resistor. Let's call it R1. When it gets to the parallel junction, it's got three options to move, right? It can either go diagonally up, it can turn right, or it can continue to move downwards. Notice how no current at all is flowing through my two parallel resistors. And that's because when the current gets to that junction, the three options are here's a road with traffic, here's another road with traffic, and here's a big open Autobahn 6-lane road that's got no cars on it, right? Just like any driver, you're going to opt for the route that has the least traffic that's going to let you go through as fast as possible. So when it gets there, all the current goes through the path that has no resistance, and none of the current goes through the path that has resistance down there. And that's a key thing to note there that this is an extreme case when I've got two resistors and one path that's got no current, no resistance, all my current is going to flow down that particular route there. You'll often see sometimes they'll give you multiple choice questions that ask you something like this. They used to like putting this question in years ago, not so much lately, but I want you guys to just be aware, right? When non-routine problems come into play, you can never say never. So just be prepared for anything and everything. Okay, let me get rid of that there, and then my circuit goes back to normal in that case. Then I'm gonna bring a voltmeter and we're gonna go have a look. Someone asked the question, why is potential difference the same, right, in parallel? So again, between any 2 points, so imagine here and measuring there. So we can see there my potential difference or my voltage is 17.68 volts, right? And if I measure here and there, depending where my terminals are looking, 17.68 volts. And I measure here and there, that's still 17.68 volts. How I like to imagine this. So let's go back to my writing pad. All right. So going back to my writing pad, I like to imagine the following scenario. So imagine I've got my cell there. There's a resistor here. Another one here, and another one here. So think about this. This is a way of thinking around electric circuits. Oh, sorry, someone did ask a question, and I'm only seeing it now. Guys, Kamahelo, please reminder, use the chat when you give me answers, but use the Q&A for questions, because now I'm missing these questions again. Okay. Someone says, what was the effect of removing the third resistor? Itumeleng, the effect on what? There's lots of effects. The effect on what in particular? So removing the third resistor, the one that was in series, lowers my resistance. It increases my current across the board. That's what happens there. Kamahelo says, what will happen if we remove the third resistor? Which third resistor? We had two in parallel, one in series. Which one should I remove? Because different things will happen depending on which one I remove, right? Let me quickly come back to then this one there. Just a quick note. I don't know, Taffy, what I believe if you guys are there. The TikTok stream seems to have gone down. Let's just maybe work on getting that one back up. Thanks, guys. This is the one in series. Yeah. So as explained there, when you remove the one in series, not much happens. You drop your total resistance and then it increases your total current across the board. So let's look at this now. So imagine I'm going to describe this. My battery is a factory, right? It's a factory that makes bread. And my current is now basically a delivery system that goes around delivering bread. So let's say I've had 10 loads of bread that were ordered, right? So my truck is going to leave with exactly 10 loads, not loaves, but loads. So 10 containers of bread inside my truck. So this truck's gonna go tum 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 tum. Before it drops a delivery off, someone says, checkpoint, please give me, they'll call them on the radio. Please tell me how many loaves you've got in your truck. And then the truck will report back. Oh, I haven't delivered yet. I haven't arrived at R1. I still have 10. So when it gets there, it says, no, I still have 10. I haven't delivered anything yet. So notice what the numbers I'm writing down is similar to my potential difference. It's my electrical potential at any given point. Then it gets to R1 and it offloads um, 6 loaves, right? So when it comes out of R1, they do another checkpoint. How many loaves do you have left? It says, oh, I dropped off 6. I've got 4 loaves left. So the truck came in with 10. It left with 4. If we put a voltmeter around here, what will that voltmeter measure? It'll say you came in at 10, you left at 4. Your potential difference, there's that word, is 6 volts. You've dropped off 6 loads or 6 deliveries of bread at this place here. So it's the difference in electrical potential. My truck will leave with 4, right? Now, I'm not going to show you what happens between R2 and R3. But remember, everything I take with me when I leave the factory, I have to come back with an empty truck. Otherwise, I was being very wasteful, right? So the truck, when it comes back into the factory, must have 0 loads of bread left. So let's now reverse time. So let's imagine we go back dim 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 to this junction over here, right? Post in the chat quickly between that junction and this potential junction here, just before it gets back, how many loads of bread did my truck have when it was sitting at this point here? What do you guys think? Quickly put your answers in the chat. How many loads of bread did I have at that point on my way back to drop off my truck back at the factory? Quickly post your answers in the chat. Okay, I'm getting different answers there. Okay, remember the direction of this truck from that point is that way. And I'm telling you, when it arrives at the factory, it has 0 left. So what would it have between here and there? Did it do any deliveries? It didn't do any deliveries, right? Trevor, thank you for your answer there, right? And Lerato as well, and Novuyo. It was 0, right? So because from here, it goes up and ends up at 0, which means at this point, it would have also had 0. That's very important. Now let's go back. So at the beginning of my parallel junction, my truck had 4 loaves. At the end of my parallel junction, my truck had 0 loaves. So if I were to do a checkpoint at this point, right? Keeping in mind, my truck had 4 loaves here. It did no deliveries here. How many loads would it have at this? Let's call this point A. How many loads would it have at point A? Trevor says 4, Lerato says 4. Well done. I would have 4 loaves at point A, right? And then again, what about point B, right? Given the fact that I had 4 here, I went down, I got to point B, I did 0 deliveries. How many would I have at point B? Lerato says 4, Trevor says 4, 100%. I would have 4 over there. Now again, let's go to the other side. I'm working my way back into my parallel junction. So we all agreed that the truck had 0 over here. If I move back to this point here, how many would I have? Given the fact that I did no deliveries here, how many would I have at this point, which we can call point C? Shanice says 0, 100%. At point C, I would have 0, right? At that point, because between this point and that point, nothing happened. So if I had 0 here, I must have 0 here as well. Similarly, the last one, let's come back down here. This is point D. How many loads would I have here? If I had 0 here and I did no deliveries here, then I must therefore also have 0 at that point, right? Okay, so now we've seen that. Now we're going to answer the question as to why potential difference is the same in parallel. If I take my voltmeter and I go measure these 2 points, I measure there and there, what's my potential difference reading going to be? I had 4 at one point. I had 0 at one point. The difference is going to be 4 minus 0. I'm going to have 4 volts. Let's do another one. Let's say I were to measure here and there, right? I had 4 at one point. I had 0 at another point. 4 minus 0 will give me 4. Let's try again. Let's go up to R2. If I were to measure there and there, I had 4 at one point. I had 0 at one point. What's the potential difference? 4 minus 0 will give me 4 volts. And that's why your potential difference in parallel is equal, but in series it's not. right? Because if I had a series junction, let's make an example of a series one where I've got a cell, a resistor, a resistor, a resistor, right? So this is R1, R2, R3. Let's say I've got a truck. Again, my truck leaves here with 12 loaves. It gets to R1. It still has 12 when it arrives. When it leaves, it's got 6, right? It leaves R1 with 6. It gets to R2 with 6 because no deliveries happened here, right? It leaves R6 with 2. It gets to R3 still with 2 because no deliveries happened here. And it leaves R3 with 0. It always has to get back to my factory with 0. Otherwise, I took more than I needed and I'm wasteful. Let's measure the potential difference there. So if I were to do potential difference from here to there, 12 minus 6 is 6 volts. Let's do R2. 1 from here, 1 from there. 6 minus 2 is 4 volts, right? Next one again there, 2 and 0. 2 minus 0 is 2 volts. So I would have used 6 volts, 4 volts, 2 volts, which must add up to my 12 volts. And you'll see if I were to put a voltmeter reading around my cell, that would give you a reading of 12 volts because your truck left there with 12 volts. And that's why when you're doing these sums, the potential difference of all your components, right? You treat a parallel component like it's one component, must add up to your V external. That's a very important thing. So if this is V total, and this is V1 and V2 and V3, V total equals V1 plus V2 plus V3. We learned about this in series, very important. But in parallel, they must all be equal. So that's just an example of how to then think through that problem. We've got 1 hour left. I'd love to start some questions now that we can do together, right? Okay, just give me thumbs up emoji, anything to tell me that you guys are still with me before we jump into the questions. If you're still a little bit unsure, don't panic. We're going to do questions now for an hour, and hopefully that will clear up a lot of worries for you guys. Okay, thanks for all the reactions there. Fantastic. Let me pause for questions quickly. And just check if our TikTok is up again, just so we don't leave those guys behind. Give me 2 seconds, guys. Okay, our TikTok stream is back up and running. Fantastic. Cool. All right, Karabo says, so particularly current prefers to flow in a fast flowing down path. A resistor connected on the middle branch of the circuit will always have a slower flow of charge, even if the resistor on that branch is higher than the rest of the resistors. If that's a question, so current always prefers to flow down the path of least resistance. So wherever you've got the smallest resistor, you'll generally tend to have the fastest current, especially when we're going into parallel spaces, right? But if it's all series, the current will be the same across the board. It'll just take all the resistors, work out what the flow is going to be, and it'll just move at that particular rate. Okay. Hope that makes sense, Karabo. Cool. Let's jump into our first question of the day. All right. So the question we've got now says, question 9, the battery in the circuit diagram below has an internal resistance of small letter r. When switch S is closed, so we can see switch S is there, there's our internal resistance. The reading on voltmeter V2, here's voltmeter V2, is 18 volts. But that is when the switch is closed. So we can see that's going to be 18 volts, right? That's the potential difference between this point and that point there. Then it also says that the resistor R dissipates 13.5 watts. So the power of R is 13.5 watts. It's 13.5 joules per second, right? Okay, and then Khosana says, so always the truck must unload all the load, return and return back empty 100%. So your potential at the end should always be zero. So your truck must always go back empty. If you go back with bread in your truck, that's going to be an overloaded circuit essentially, and you can't really have that. Your cell is going to burn up if that happens. So you always go back with zero at that in that scenario. Now we've unpacked this question here. Let's look at the questions, right? Question one says state Ohm's law in words. I'm going to give you guys a chance to put that answer in the chat. State Ohm's law in words. I'll give you guys a minute to type that in the chat. If you've just joined us on TikTok or even on Zoom, we're busy with this electric circuits question. Please answer 9.1 in the chat, and then we'll give you the correct answer just now. State Ohm's law in words. Okay. Let's quickly look at the answer together. So Ohm's law states that the potential difference is directly proportional to the current, provided the temperature remains constant. Right? That's going to be your Ohm's law definition in that case there. Let's jump on to 9.2. Okay. Thank you very much to Luyanda, Kabelo, Kiloachile, and Itumeleng for your guys' answers. You guys are awesome there. Okay. 9.2 says calculate the resistance of resistor R. So we got given this information here. We were told that the potential difference around R is 18 volts. We were also told that the power dissipated by R is 13.5 watts. We need to find the resistance of R. So we've got power, we've got V, potential difference. We have to find the resistance, right? So let's think of an equation that's going to have two of those values and as well as the value we're looking for. We're looking for R, we've got V, we've got P. We're looking for P, V, and R. The equation in question is going to be P equals V squared over R. And in this case here, we're trying to solve for R, right? So let's plug our values in and see how far we get. So P is power. We were told that power was 13.5 watts. So we'll quickly plug that in. 13.5 is equal to V squared. So the V, we were told as our potential difference is going to be 18 volts. So let's substitute that in there. 18 squared divided by R. And we want to solve for R. So we're going to make R the subject of the formula. So we're going to then multiply both sides by R, divide both sides by 13.5, and then you would get something that looks like this. R equals 18 squared divided by 13.5. And then if you guys can pop that into your calculator, quickly do the calculation and post an answer for me. Thanks, Luyanda, Nitumeleng, and Kabelo, and Pakiso as well. Thanks, Ravane. Thanks, Abakwe. Okay, fantastic. So everyone's getting the answer that I'm seeing there. You're going to get 25 ohms. No, sorry, 24. Okay, hope that made sense. If you got the right answer, please give yourselves some dancing emojis, fire emojis in the chat there to celebrate. If you didn't get it right, but you see where you went wrong, or you now see how it's done, that's cause for celebration. You've learned something, and it's not a mistake you'll make in your exam coming up. So you guys can celebrate as well. Awesome. Thanks, guys. You guys are awesome. Let's look at 9.3. 9.3 says, calculate the reading on the ammeter. Okay, the ammeter is this one over here, ammeter A. Now let's pause and try and get a game plan together, right? So how are we going to get the information on that ammeter? One of the ways we can do it is, well, we know that V is equal to IR, so I is equal to V over R, right? So if I is equal to V over R, if we could find the V external and divide it by the total resistance, that could give us I. That's one way of doing it. Another way of doing it, remember, current in equals current out. So current in is here, current out are these two here. If we could find this current and that current, add them together, it would give us this current. That's another way of doing this particular problem, right? And then once we've done that, we can then find an answer. So any one of the two solutions will work. I think I prefer the option of simply finding the two current values and then I'll add them together, right? So let's quickly do that. So how do we do that? To find the current, we're going to start here. We know we worked out the resistance. We worked out the potential difference. I mean, we were given potential difference. We can find the current. One thing I'll always recommend, guys, if you want to find a value, rather use values you were given before using values you calculated. Because if you made a mistake, you're going to lose marks. So take the values that you were given and use this P and this V to find the I, right? That's what I'm going to do. So I'm going to find the current that flows through here first using P is equal to the IV. So let's do that as our first step. So P is equal to I times V, right? It's the power through that other resistor. So it's going to be 13.5 is the power that was given to us. Let's substitute. That's going to be the 13.5 is equal to I. We're trying to solve for I. And the V was given to us as, I think it was 18, right? So I is equal to 13.5 divided by 18. And if you put that together there, you should get an answer of 0.75. Okay. Double check it on my side there. 100%. 0.75 is the answer we're looking for there. So my current 0.75, and that's the current through my resistor R, right? Let's call that current through resistor R. So now we've got that. So this is going to be 0.75. That's my current there, amps. I need to find the current now in this branch, right? To find the current in this branch, I need the values for this branch. So what do we know about the potential difference of the 12 ohm branch? So if I put a voltmeter here, what would the value of that voltage be? Elizabeth, thank you so much. I will do that. I'd forgotten there. Same voltage, Novuyo, same as what voltage? Thanks, Itumeleng, 18 volts, right? Because it's parallel, they will have the same potential difference on the two branches. Thank you, I'd forgotten to do this there. Amps, perfect. So to find this current of the 12 ohm resistor, I'm going to use this 18 volts because it'll be the same potential difference there. And then I can find my current in that case there. So let's quickly go and do that. So first I need to find the current. So the current V is equal to I times R. My potential difference is going to be 18, right? Because it's parallel, they will be the same. The current is what I'm trying to solve, and the R was given to us as 12 ohms, right? So when I solve and make I the subject of the formula, I get 18 divided by 12. Quickly plug that in and give me an answer. Okay. Okay, just wondering, some people are writing 216. I just want to make sure, check where you guys are getting that particular answer. So the answer you should have here is your current there should be 1.5 amps. That's the current you should be getting. 18 divided by 12 is 1.5 amps. And for me to then find my total current, which is the current I've been asked to solve in this problem, is going to be I1, which is what I found, plus I2, and that will be 0.75 plus 1.5 amps. And that should give you, a lot of you guys got that final answer, 2.25 amps. Okay. Let me quickly pause for questions. Bonola says, so the potential difference in parallel is equal. Yes, Bonola, 100%. In a parallel circuit, the potential difference of each branch will be equal. So what's the mark allocation? Because if we use I is equal to V over R, we get this exact same answer. So the mark allocation is 5 marks. So I did say that you can, so when I was busy at the top there, you got two options. You can find the current in each of them, solve, or you can use Ohm's law, V is equal to IR. The only thing to note there is you must first find your total resistance, right? Which we hadn't done first. So that would require you to then say, oh, let's first find R parallel. Once you find R parallel, add that to 10, and then that is going to give you your answer for your R total, essentially, right? Then you must think about, actually, no, you don't even have to add it there. You literally can just use R parallel, and the potential difference across R parallel, actually. You don't even need to go at the 10, and then that should give you the answer you're looking for at the end. So if you use that, you'll get the same number of marks, 5. Okay. Awesome. Novia says, can we also use a ratio to find the current? We can, but I'm very curious, Novia, as to how exactly you would do it. So would you like to maybe unmute and tell us how you would solve it? I can maybe give you permissions to unmute. Novia, let me search for your name. Okay, Navuyo, I've given you permission to talk. You can unmute and maybe give us a shout as to how you would have used ratios to solve that one. Sorry for putting you on the spot. If you don't want to, I perfectly understand. Don't stress about it at all. But if you'd like to share, then please just unmute and you can share how you would have used ratios to find that current. In the meantime, Trevor says, why don't we use 10? Trevor, help me understand. Oh, the 10 ohm resistor, because Navuyo, are you there?
Yes, I'm here.
Oh, perfect. Sorry, let's quickly, before I respond to Trevor, quickly walk us through how you would use ratios to solve for the current there.
I thought maybe like I could say like 18 is to 24. Then find common factor between the two, which is then going to be 3 is to 4. Then
18
we
is to 24.
yes,
Please just walk me through what is the 18, what is the 24? So what ratios are you comparing?
the resistance.
Um, so that's the resistance. 24 ohms is this resistor here. Let me just quickly write this down. So this is going to be 24 ohms, right? So 18 and
Yes.
to 24 will be a ratio that will give you an indication of current,
Oh, no,
100%. And then what would you
12,
do as
12.
well on the other side?
It's going to be 12, sorry, no?
It's going to be,
12 and 24. My mistake.
okay, sorry, walk me again, 12 and 24. Oh, the ratio of your resistors.
Yes. The ratio is
And
going
then
to be
you
12 is to 24.
12 is to 24, and then you take that and do what with that?
And then the common factor would be 12, which is then going to be 1 is to 2.
Yes,
Then we already calculated current and we found that it is 0.75.
yes,
And we could let the current for the 24 ohm resistor be X. Then we
yes.
cross multiply and get and say 0.75 multiplied by 2 and get 1.5.
Okay, and that's to get the current in the 12 ohm resistor. Let me quickly repeat it for those that are not necessarily following, right? So
Thank you.
how Novo is saying we should go about this. So step one, right, is we have to do the first same step. So you have to first find the current through resistor R, the 24 ohm resistor. Then after that, she wants to then use a ratio because remember, current splits always in proportion to the ratios of the resistances. So she then says, okay, well, we're going to have 24 over 12, right? Novuyo is equal to, what did you say your other ratio was going to be on the other side? Novuyo, you're muted. Sorry, I want you to walk me through so I can write it the way you were saying it.
Yes, sir.
You said 24 over 12, and that ratio will
Yes.
then give you what on the other side?
1:2.
It'll give you 1:2, right?
Yes, sir.
Or in this case, I wrote it the other way, so it'll be 2:1.
Is
And you're going
one.
to
Yes.
equate that to what exactly?
Then we know that current for one would be 0.75,
Yes.
and then we let the one at the top be X.
Okay. And so one thing I want you to note that's going to be very important, right, is that you need to know, because one thing that's tricky here, the 24 ohm resistor did not have X as current. It had 0.75 as current, right?
Okay.
And then the 12 had X as current. So I want to just help you. If you want to use this in an exam, I want to help you lay it out in the best possible way, right?
Okay.
So
Yes.
you're saying, so here's one thing I want you to remember. So here are the steps that I would like you to use. So you're going to go back to your theory and say, oh, remember, Ohm's law says V equals I times R. What we know is that the potential difference of branch one is equal to the potential difference of branch two, right? So we know
Yes.
that I times R of branch one is equal to I times R of branch two. Are you with me?
Yes, sir.
Let's substitute our values, right? So branch one had 24 ohms, and we already worked out the current is 0.75, right? So we'll then plug that in. So we'll say that's 24 ohms. And sorry, I wrote it the other way around. My current is 0.75 and 24 ohms. Branch 2, we're trying to find the current. I'll leave it as I2, but I know that my resistance is 12. And now I can solve for I2 by making I2 the subject of the formula. So in that case there, I'm going to have I2. So from there, I'm going to just go up there. I2 is equal to 0.75 times 24 divided by 12. And that should give you the same answer that we had
Yes.
previously of 1.5
Comma
amps.
five.
So 100% well done for using a different method. And I think as what I want to show and appreciate everyone is that there's no one method that's better than another method, right? The method that's best is the method that you can remember. That's always the best method. So don't let someone come and tell you, no, 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 that method is bad. Here's the better method. No, the best method is the method you can remember in an exam. That is the best method. And for us, they might be different, and that's okay. There's no bad method, there's no good method. If it gets you to the right answer, that is the best method. Full stop. The only thing I wanted to help you with here is how to lay out your answer. Because remember, when examiners are sitting, they're sitting with a memo that's giving them option one, option two, option three, option four. And you want to make sure that you lay out your work in a way that they don't think, this person does not know what they're talking about. And you don't want to make them think that you fluked your way to an answer. So always lay your work out in a very clear manner to say, well, I know that Ohm's law is V is equal to IR. And because they're in parallel, the V of branch one is equal to the V of branch two. Then you can write there IR1 equals IR2. Substitute because it'll do the ratio for you. It's the exact same thing that you're doing. And then you can go there as well. Okay. Awesome. So hope that helps you guys quite a bit. Someone there, the B says, "Can I try?" I'm sorry, the B. Unfortunately, we there's no easy way for me to get someone on TikTok to engage on Zoom because the platform, the lesson is running on Zoom. We just stream to TikTok so that we can try and involve and pull people in. I don't know if it's possible. If whatever you can post the Zoom link somewhere on TikTok so people can then join across. If you're on Zoom, more than welcome. You can put up a hand, you can speak, you can do whatever. That'll help you quite a bit. Someone said, please zoom out so I can take a screenshot. Anonymous, please remember, I will be sharing these notes in our WhatsApp community. So you can get all of this, but I did zoom out there for you. Okay. All right, let's move on to the next question. I'm going to just draw a line so we remember that this is a different method to what we started off with. And then just write the alternative method. Novia, thank you so much. I'm going to remove your ability to unmute. But again, thank you for the engagement. If you do want to engage and ask your question live, just put a hand up, and then I'll also just allow you to ask live. But thanks, Novia, for that. I really appreciate it. Okay, let's look at question 9.4. 9.4 then says, explain in words what is meant by the term internal resistance of a battery. Right? So like I told you guys before, just to get you to understand it, it's the energy required to get the the electrons and the charge out of the battery. But in this case here, you have to use now proper definitions, right? So you have to go use the definition of resistance. So internal resistance is the opposition of the flow of charge within a battery. That's your internal resistance, right? Hope that makes sense there to you guys. I'm going to quickly paste it so that you guys can see it. So internal resistance is the opposition of flow of charge within a battery. But how I wanted you guys to think about it, it's what you need to get those electrons out. There's a cost to getting some of those things out there. All right, hope that makes sense. Trevor put a question mark. Oh, you're asking why we don't use 10? Trevor, so like I said before, sorry, I had answered the question. I don't know, maybe you didn't hear me, right? Is that in this case here, the other method was to do V is equal to IR for the entire circuit. I said we can stay with the parallel component. Find your parallel resistance and use your parallel what's this? Potential difference to find out what current goes into my parallel junction. We don't even need to use that 10. We can just use these factors here. That's why we don't use the 10. Sorry, Trevor. I said your question was answered. I thought you had heard me when I answered it earlier. And then Anonymous says, so what is the mark distribution for the ratio method? It'll be the same. If I try and figure out how they'll allocate the marks. So generally what they will do there is you will get a mark for the equation, right? Be it the first or the second one. You will then get marks for substitution, right? In that case there, and then you'll get a mark for the final answer, right? So they'll give you a mark for, oh, you must, oh, sorry. The last thing we need to remember that you must still do this step down here because all that does, all the ratio method does, it substitutes this here. It just helps you find the middle answer. You still need to go back and do the last step at the end of the day. So there'll be a mark for equation, mark for substitution, and then a mark for your final answers. And that's how you get the 5 marks allocated in this particular question, right? Okay, hope that makes sense to you guys. Okay. 9.5, calculate the potential difference across the 10 ohm resistor. So potential difference across the 10 ohm resistor, it's this one here. Potential difference is V, that's equal to I times R. We now know what our current is, right? Because if I look at my current, this is what I also like doing, is I do a map of what my current looks like. So out of my cell, my current is yellow, it goes down, this value will be yellow. It gets there, it's gonna split, right? When it splits, it becomes, for example, orange until there, and then maybe also pink until there. Yellow split up to become orange and pink. Orange and pink must come back together to form yellow. And then that happens there. So what we can see there is the current through the 10 ohm resistor is the same current we worked out on the other side, the ammeter A. So we can use that current and that resistance to find the potential difference. So we've got a current that we worked out, which is 2.25, and we've got a resistance of 10. We can use that to find my potential difference. So let's quickly go do that. Not a difficult sum to do. So V is equal to I times R. Let's substitute. My current, we did work it out in the previous question. That's 2,25. My resistance is 10 ohms. It was given to me. Plug that into your calculator, and you should get a very simple answer of 22,5 without even having to plug it into your calculator. You'll get the value. of the potential difference across the 10 ohm resistor. Thank you for your answers there, E2, Zizi, Kabelo, and Luyanda. You guys are awesome. If you got that question right, please give yourselves a round of applause. Celebrate with your reactions, with your emojis. If you didn't necessarily get it right or you didn't finish on time, but you see how it's done and it makes sense to you, please go ahead and celebrate there as well. Okay, fantastic. Let's jump on to 9.6, right? So 9.6 says, when switch S was opened, the reading on voltmeter V1 was 45.9. Remember, this is coming back now. We spoke about this at the beginning of the lesson, open switch versus closed switch. So we go back here, we can see there's a switch in my circuit here, right? So what we're told is that when the switch is open, voltmeter V1 reads, where is this question? 45.9 volts. All right. So my question is, and please put your answers in the chat. When the switch is open and no current is flowing, voltmeter V1, is it going to give us the reading of EMF? Itumelong, I haven't even finished my answer, Trevor, or V external. All right. Thanks to all the quick fingers. I'm not saying you guys are right, but I want you guys to put your answers in the chat. So when my switch is opened, is V1 going to read EMF or is V1 going to read V external? So when I open this switch, what will this give me? EMF or V external? Put your answers in the chat. Okay. I'll give you guys 10 more seconds to quickly pop your answers in there. 5, 4, 3, 2, and 1. Well done, guys. The correct answer is when you have an open switch, you're going to get a reading of EMF from this voltmeter that's sitting around my cell. Very, very important. If you got the right answer, give us those awesome reactions celebrating. If you didn't, but now you've remembered, oh, that is the correct answer, and you won't forget it for your exam, you can also jump into the celebrations because you've learned something new and you're not going to make this mistake in your exams, right? So when the switch is opened, the reading was 45.9. We know that that is actually our EMF, 45.9 volts. Okay. Then they said, calculate the internal resistance of the battery, right? So now we need to go work out the internal resistance of the battery. Keeping in mind, before I go back up, that we know there's two equations we can possibly use. We know that EMF equals I into R plus R, or we can say EMF equals V external plus V lost, right? So those are the two equations we can use to find our internal resistance. We can either use the top equation, find our value for that, and solve for this, or we can just find V lost and then divide that by the current that flows through the entire circuit. The method that I think I'm going to prefer to use is simply to be one where I've got my current in my circuit. We worked out the current, that's this value here. I can work out my R total. And then in that case there, I can solve for this there because I've got my EMF. So I'm going to choose the option of finding my total resistance and then plugging the values in. That's the option that I'm going to choose, right? So I'm going to use this equation over here. So let's first find our total resistance. To do that, we need to first find our R parallel. So let's quickly find our R parallel. So 1 over R parallel equals 1 over R1 plus 1 over R2. If you remember the values of our parallel resistance, we had 12 ohms and 24 ohms, right? So that's going to be 1 over R parallel equals 1 over 12 plus 1 over 24. To then get that into our calculators, we need to then simplify the right-hand side. So 1 over R parallel equals 2 over 24 plus 1 over 24. So that's going to just be 3 over 24, right? And then flip both fractions. R parallel equals 24 over 3, which is 8 ohms, right? So R parallel is going to be 8 ohms. To get R total, we need to add this to that, right? To get our total resistance of the entire setup. So to then do that, we find R total. R total equals R parallel plus R in series. R parallel we worked out to be 8 ohms. R in series is simply 10 ohms. We saw it up there. It was simply given to us there, right? So let's quickly plug those values in. That's going to give us 18 ohms. That's my R total, my external resistance. Now I can go and solve my equation, right? And we're going to start in that case there. So that's EMF is equal to I into R plus R. Our EMF was given to us as 45.9 volts. Let's substitute. That's 45,9. The total current in our circuit, we did calculate that previously. That was at 2.25, right? 2,25. Open bracket total resistance, we worked that out. That's 18 plus R like that there, right? So then to find R, let's quickly work this. So we know that we're going to first have 45,9 divided by 2,25. That's equal to 18 plus R. Make R the subject of the formula. R equals 45,9 divided by 2,25 minus 18. Plug that into your guys' calculators, and then you can tell me what answer you get. Okay, there's a lot of quick fingers there. Thanks to Pakiso, Kabelo, Itumeleng, Zizi, Palesa, Lerato, everyone there between. Okay, and the final answer we get is 2,4 ohms. That is our internal resistance, right? Okay, quickly, Kosana says, "Sir, I'm lost." 9.3. That was our final answer, 2,25. It's the current, this yellow current through my circuit. That's where I'm getting that 2,25 from. So I'm simply going to just take my sum there. EMF was given to us in this question. We were told when switch S is opened, the voltmeter reading is 45,9. That's where the 45,9 comes from. The 2,25 comes from 9.3 when we had to work out the total current in the circuit, the reading through ammeter A. My total resistance is going to be a combination of my parallel resistance, which is 8, including my series, which is 10, will give me 18 ohms. That's where I get this 18 from. And then finally, I've got an R, which I'm solving for. At that point, it's just algebra to solve for R. Okay. Khosan, I hope that makes sense to you there. And I know Mr. Tendi says V external. I don't know what that means in particular. I don't know. I can't even ask you to unmute because your name isn't there, so I can't ask you to unmute. I think you didn't log in. I'm not sure what's going on. All right. Cool. Hope that makes sense. If you got the question right, let's do our big celebrations. If you didn't get it right, but you see where you went wrong, you can jump straight in and do what you need to do, right? So Novi is asking, is our V external also 45.9? No, Novi, it's not. If you do have internal resistance, your V external will always be less than EMF. So it'll be something lower than 45.9, right? We can work it out, but we don't need to work it out in this particular problem. But yeah, EMF will always be more than V external. V external will always be less because remember, that's why we have lost volts. Some of it will be used up. If I have internal resistance, their values will not be the same. Okay, and then someone says there, alternative to calculate parallel resistance, this is from Itumeleng, is that R1 times R2 divided by R1 plus R2, 100%. We can definitely go ahead and do that, and then that will give us the very same answer. Thanks for that, Itumeleng. I'll quickly put that down on here as well. So we could say R parallel equals R1 plus R2, right? Which is going to be, not plus times, 12 times 24 divided by 12 plus 24. And if you plug that in, that should still give you 8 ohms. Thank you for that, Itumeleng. Very useful. Okay, Anonymous says, please do the other equation, the one that you said EMF is equal to V external plus V lost. Okay, 100%, I'll do that for you. I just need to find space. Let me do this. Let me add a page and move this other question down. Okay, so if we do the V external plus V lost equation, all right? Basically what we need to then do there is the key point there is to find what is V lost. That's the main thing, right? So to do that, I need to find what is V lost. So to find V external, right? Let me do another line. Let's say, or. So to find V external, it's going to be I total times R total. I've got I total. I need to find R total. So to find R total, you're going to use this method up there, right? So you're going to use that method up there. And then you can say, well, my V external equals 2,25, which is our I total, times my R total, which was 18, right? And then your V external should be, sorry, grab my calculator quickly. 2,25 times 18 gives me 40.5, right? Thanks, Gabelo there. So I get 40,5. Now I need to find my V lost. So we know that EMF equals V external plus V lost. So which means here my V lost equals EMF minus V external, right? And in that case there, we're dealing with, what's my EMF? 45.9 minus my V lost, which is 40.5. That will give me a value of 5.4. That's my V lost. And then how do we work out V lost? Simple. V lost equals the current times my internal resistance. Then we can sub those values in. My V lost is 5,4. The current is 2,25. And I need to solve for small letter r. Small letter r will be 5,4 divided by 2,25. And then the final answer for r will be exactly the same, 2,4. That's the alternative method. That helps. Okay. Anonymous, hope that makes sense for you guys there. Then I can jump on to the next question. All right. Nine 9.7, does the internal resistance in the circuit increase, decrease, or remain the same when resistor R is removed? Please give me your answers. You don't need to give a reason, but I will give you the reason when I give you guys the correct answer. Does the internal resistance in the circuit increase, decrease, or remain the same when resistor R is removed? Thanks, Zizi, for your quick fingers. Not saying you're correct, just saying thank you. Thanks, Itu. Thanks, Trevor. Thanks, Shanice. Thanks, Nzelo. Thanks, Novuyo. Thanks, Mpilonhle. Thanks, Palisa. Thanks, Moon. Thanks, Muko. Thanks, Rubaune. Thanks, Shanice. Okay, 5 more seconds, guys. This is a multiple choice question. Never leave multiple choice questions empty. As Tapang would say, for those of you who join the math sessions as well, you miss 100% of the chances you don't take. So don't leave this chance to go, right? Okay, thanks. Khosana Bakwe, Kabelo Lerato as well, right? So the correct answer for this one is going to be, drum roll please, remains the same. Okay. And reason why, remember, they're not asking us about the lost volts, they're asking about the internal resistance. It's the same as me asking you, what will happen to the resistance of R if I remove the 12 ohm resistor? Nothing. The resistance of a resistor, it's not a variable resistor, it's a fixed resistance. Even your internal resistance is a fixed resistance. If I remove this 10 ohm, it doesn't affect the 12 ohm, it doesn't affect this R. The value will be exactly the same, nothing will change, right? So they were tricking you guys into thinking they're asking about lost volts, but they didn't. They just asked about what happens to that resistor. And another key thing to note, it's a 1 mark question, right? And they didn't ask you to explain why, because it was straightforward. Changing one resistor is not going to affect the other resistor because they're not asking about potential difference or current or anything like that. Awesome. That's a nice little one there. We've got 15 minutes to go. I do have another question. I don't know if we'll manage to finish it all, but would you guys like me to start that question? Here's a quick question. Quickly post in the chat. Should I start the next question? Just post your answers in the chat. Or you want to stop and just do a Q&A? Okay, lots of yeses coming in on the Zoom chat there. TikTok gang, you guys are quiet. Do you want me to do another question or are you guys covered for today? Okay, TikTok guy said no, so we'll stop the live. I'm joking. And then, okay, everyone else is saying, yes, can we attempt it? Okay, fantastic. Someone saying recap. I think a recap, the best way to do a recap is to do these questions, to do another set of questions, because we get to recap the methodologies. The theory in electric circuits sometimes can feel very far from the reality. You need to do the work to actually understand it. It's not like more theoretical based chemistry stuff. You need to actually do the problems here. So that's fine. I got enough yeses to say let's do it. So let's move on. And we've got 13 minutes. I'm going to try and move a little bit faster with this question, and then let's see how far we get, right? Awesome. So here we see 3 resistors and an electrical device rated 16 watts are connected to a battery of EMF 36 volts. An unknown internal resistance R, as shown in the circuit diagram below. Emitter A2 reads 2 amps when the switch S is closed. First thing I want to do, I want to identify where my currents are, right? So I've got yellow current coming out of my battery. It gets to a junction, it's going to split. So it'll split to orange. Oh, sorry. It'll split to orange. So A2 will be orange current, orange. It'll get to another junction where it has to join back with the other current. Where it originally split was orange and pink. Orange and pink come from yellow. So when they come back together, they must go back to yellow. So emitter A1 is going to be yellow. So if I want a current reading that's in yellow, I look at emitter A1. If I want a current reading for anything in orange, I look at emitter A2, right? Okay. Define the term EMF of a battery in words. That's fine. We can quickly do that. I'm going to go through the definitions quickly so we don't waste time, right? So defining the EMF of a battery, it's defined as the total energy per coulomb of charge that a battery can supply, right? Let me quickly paste that in there for you guys. The total energy per coulomb of charge that a battery can supply. That's 8.1. Thank you for all the quick fingers there. You guys are awesome. 8.2, calculate the resistance of the electrical device, right? So we're looking at the electrical device there. We were given power of that device, 16 watts. We also know that the current is 2 amps because we can see there, the current through here is the orange current, and the orange current is going to be 2 amps. So we've got power, we've got current, we can solve for the resistance. So let's quickly work out that. An equation with P, I, and R is going to be the following. P is equal to I squared R, right? And then we can simply substitute the values we've got there. We were told the power is 16 watts. Don't know why I put that in brackets. The current we were told there was 2 amps. That needs to be put in brackets and squared, and we're solving for R. making R the subject of the formula, we have R is equal to 16 divided by 2 squared. 16 divided by 4 will give us a very simple answer of 4. Oh, thanks, Shanice and Elizabeth, there for your quick fingers and your correct answer, right? Awesome, guys. Let's jump on to the next one, 8.2.2. 8.2.1 was nice and easy. Then they want the current passing through the battery. Let's quickly go back and have a look at this question here, right? So how do we get the current passing through the battery? The current passing through the battery is going to be the current A1, right? So to find the current A1, there's a number of things that we can do there, right? So to find the current passing through the battery, what we can do is we can maybe find the total resistance, but we don't have the V external. So that's not really going to help us. What we could do there is we could find the potential difference in the orange side and then find the current A2. If we can find current A2, we've got current A2. If we can find current A1, add it to current A2, we will then be able to get that value of the current going through the battery. So the steps I'm going to follow at this point here, I'm first going to find the potential difference of the parallel component, right? Once I find the potential difference of the parallel component, right, I can then go and find the current through the pink part. Because remember, this current here plus this current here equals this current here. I already have this current, it's 2 amps. I just need to find this current here. And because I know that the potential difference here and potential difference here will be equal, I can use the information I've been given to find the potential difference here and use that to get the potential difference there. So let's start by doing that and finding the potential difference in the orange side of my circuit, right? So to do that there, let's say R is equal to V over I, or V is equal to IR, however you want to put it, right? So R is equal to V over I in that case there. So my potential difference is what I'm trying to solve. So the resistance on that side there, we've got 8 ohms plus my device has got 4 ohms. So it's going to be 8, sorry about that. It's going to be this 8 plus this 4 to give me 12, right? So that's going to be there. 8 plus 4, that's my R. My V is what I'm trying to solve for, right? And my I is going to be given to me, it was given to me as 2 in that case there. So 8 plus 4 is 12 times 2 will then give me 24 volts. So that's my first thing there. I now know that the potential difference here, if I were to put a voltmeter this way, where's my marker? There we go. If I were to put a voltmeter this way, that would give me 12 volts, right? And now what I know about that as well is that that 12 volts will be the exact same 12 volts if I were to put a voltmeter here. That will also give me 12 volts. And that will allow me to solve for the current through this channel over here. Okay, so let's quickly go and do that. Let's find the current through the 10 ohm resistor. So the current through my 10 ohm resistor, I is equal to V over R, right? Is equal to V over R. The V we solved from before, it's going to be my 24 volts. Did I write 12 in the previous one? Sorry, 24 volts. 24 volts. My resistance is 10 ohms. Yes, it's 10 ohms. Meaning the current there will be 2,4 amps. Okay, and now to find my I total, I'll just need to add both of my currents, right? So in that case there, equals I1 plus I2. That's going to be 2,4 plus 2, which gives me 4,4 amps. And that's the current that goes through my battery. Thanks, Shanice, for that answer. Well done on that one there. Hope that makes sense, guys. I know I am moving a little bit quick through this question because I want to just get to the end of it, especially the next part there before the end of our lesson. 8.2.3, right? Before I move on, there's a question that says, so where does 8 plus 4 come from? 100%, that's a good question. So 8.4 is the resistance I'm dealing with there, right? This 8.4. So what I need to go do there is come back and look at what's happening in this case. So when I'm looking at my circuit, this orange part of the circuit, I want to find my total resistance for this branch there. So in that branch there, this is an 8 ohm resistor. Our device had 4 ohms of resistance. We worked it out in the previous question. Let me quickly show you guys now. We worked it out there. So if I take that 4 and add the 8, that gives me my 8 plus 4, which is 12, that I then used in this question here. Hope that makes sense to you guys, right? Let's quickly go ahead and move on to the next question. Now the next question says we need to find the internal resistance of our battery. So in order to do that, we need to then try and think of a few things. Just give me 2 seconds, guys. I want to just quickly, my pencil was down. I want to quickly just charge it. Okay. So the internal resistance of my battery, for me to go and be able to find that value there for 8.2.3, right? I need to think about a number of things. So like we saw last time, I can either do the way of finding my lost volts and then the current, or I can do the way of finding by total resistance, current, and then solving it that way, right? How I want to do it, I'm going to do the total resistance method and then solve it. The same method I used last time. I think I find it to be a lot easier. So let's put our equation down and then work at it step by step. So the final equation I'm going to use here is EMF is equal to total current times total resistance plus internal resistance. In this case here, when I'm looking at the values, do I have a value for EMF? Yes, I was given 36 there, so I've got a value for EMF. Do I have a value for current? We just worked out the value for current. Do I have a value for total resistance? Not yet, but I can find that, right? So let's quickly find that value for total resistance. So when looking at our diagram, so we've got a parallel circuit plus a series circuit. So we must go and find the parallel resistance, then find the series resistance there. Let's go ahead and do that. So to find my R parallel, 1 over R parallel equals 1 over R1, which is branch 1, plus 1 over R2, which is branch 2. So let's keep that going. My branch 1 has 8 and 4, right? So let's put that down, make sure we've got that together. So that's 1 over 8 plus 4, plus my other branch then has a resistance of 10 ohms. Let's go and do that. That's 1 over 10. Then I can go and solve for that. So that's going to be 1 over 12 plus 1 over 10. I'm not going to find the lowest common denominator, but I can just say 120, right? So that's going to be, let me put that there in my calculator. So 1 over 12 divided by 1 over, plus 1 over 10 will give us the following. Plus 1 over 10. If you put that in your calculator, you get 11 over 60. 11 over 60. And then you can flip that over. 60 divided by 11 should give you a value of 5.45, right? So that's going to be R parallel equals 5.45 ohms. Okay, thanks for the quick fingers there. Now I know my R parallel. I need to find my R total, right? So R total equals R parallel plus R in series. We just find R parallel. It's going to be 5.45. My series R, we saw is going to be this here, which is 2 ohms, right? So let's add that together. So 5,45 plus 2 ohms equals 7,45 ohms. Now I've got my R total, which is the value I was missing here. I can actually go solve my problem, which is solving for this unknown here. Let's substitute our values. So EMF, we were given the EMF value. If you go back to the question, we were told that our EMF is going to be 36 volts. So let's substitute that in there. So we've got 36 volts is equal to the current. We worked out the current in a previous question. I total is going to be that 4.4, right? There we see it in the previous question. So let's do that. Plug that in. That's 4,4. R total, we just worked it out. That's going to be 7,45 plus small letter r, and then we can solve. To solve small letter r, let's make it the subject of the formula. So we're going to start off with 36 divided by 4,4 is equal to 7,45 plus r, making r the subject by itself. R then becomes 36 divided by 4,4 minus 7,45. And if you plug that into your calculator, a lot of you guys have already gotten that answer down. You will find that small letter r, our internal resistance, is equal to 0,73 ohms. Well done to those who got it. Well done there. And then someone there says, can we use the other equation? Let me see how many questions are left. Okay, so using the other equation, the V lost method, right? We can. So in that case there, to find V lost, we need to find out V external first, right? In that case there. So how we go about doing that, to find out V external, the methods, we can either add up the voltage across the entire thing there. That'll give us our V external. Or we take our total resistance divided by our total current. And that's just the easy way of doing that. And then that'll find you your V external and then your V lost, and then you can solve it that way, right? It doesn't make a huge difference. It might actually be a little bit longer doing it that way, but we're more than welcome to do it. So to find your V lost, you know that your EMF is equal to V external plus V lost, right? So to V lost is going to be Vx is going to be EMF minus V external. So to find V external, we have our R total somewhere there, right? And if we use V is equal to IR, we'll get our V external in that case there. So for V external, so V is equal to I total times R total. I total, we have a value of, what was it, 4.4. R total, we had a value of 7.45. That will give us, quickly work it out, 7.45 times 4.4, 32.78. So then from there, we can find our V lost, right? So V lost equals EMF minus V external. EMF was given as 36. V lost is 32.78. So let's do that. 36 minus 32.78. We get our V lost as 3.22, right? And then we know finally that V lost is equal to I times small letter r. So 3,22 equals 4,4 times small letter r. Small letter r equals 3,22 divided by 4,4. And then if you put that in your calculator, you get 0,73. Same answer. 0,73 ohms. Okay. Hope that makes sense. Hazel says, can we have an additional hour? Unfortunately, not Hazel. On our side, we do have to wrap up the lesson right now. I hope it was useful. I feel like we did a lot in the lesson, right? If you want to do more practice, just go download extra past papers and then you can rewatch the lesson. We're gonna have it up on our YouTube pretty soon, just for you guys to be able to rewatch, guys. But it has been an absolute pleasure working with you guys.